Another important class of simple convolutions that we can look at are ones involving some decaying exponential sequence, and then maybe integrating that with a box or another decaying exponential sequence. So we'd like to be able to manually compute some convolutions like this in the time domain, and then use standard formulas like the geometric series to simplify your output calculation. So let's look at a example. So suppose we have the signal x of n, which is minus a third to the n u of n. So it's alternating sign. It goes from 1 to minus a third, then to a ninth, then minus 1/27th, and so on. And then I have a box that goes from 0 to 9. So it goes u of n minus u of n minus 10. So this is a box from 0 to 9. Right, and so I can write these in formulas. I can write this. This is obviously the same formula as up here. And then I can write h of n in terms of a sum of delta functions if I want m equals 0 to 9. That is a different way of writing it. So these are all equivalent representations of the same signal. Sometimes it's more convenient to use one than the other. Okay, so what we can do is we can write out the convolution explicitly. We can substitute x and h into the convolution formula, and then use the step function, this u, to simplify the limits. So what does that look like? So we're going to write x of k here. Now we're writing x of k, and then we're going to write h of n minus k. So now because I write the h in terms of a summation itself. So there's a summation from m equals 0 to 9, and now I get this like 3-term delta function. And over here I have the same minus 1/3 to the k, u of k. That's pretty straightforward. And I'm summing again over k from minus infinity to infinity. So this u of k, remember, is equal to 0 if k is less than 0. So we get this limit only from 0 to infinity. I can pull this other summation out to get this summation here, and then I have delta of n minus k minus m times minus 1/3 to the k, and I have this sum over m. So now we can play around with this delta function, which is called, the Kronecker delta function. So basically, delta of stuff is equal to 1 if and only if the stuff equals 0. So I basically need to figure out when this thing is equal to 0, and that's equivalent to saying k is equal to n minus m. So now we have two regimes. We basically have n going from 0 to 9, which is kind of if you think about it, it is when you slide, it's kind of the partial overlap scenario from our 5-phase method. And then once it's slid fully across this decaying exponential, then we'll get a term that goes from n minus 9 to n. So now we're just going to be essentially summing up this exponential sequence. We're summing up different parts of it, right? So remember, maybe if we draw a picture, we have this, 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 this. So basically, we're sliding over our box, and we get initial period of partial overlap until the box is until the x here, the h here, rather, is completely in the system, and then we're just going to get partial sums of length 10 of this discrete time sequence. So we can simplify these sums using the geometric series, and I guess it's important to remember these formulas. It's worth writing them down in case you want to reference them in a quiz or something. Basically, they all stem from this basic geometric series, which says you have a sum of powers, and as long as the alpha is less than 1, magnitude of alpha is less than 1, then it's equal to 1 over 1 minus alpha. And from there, you can derive all of these partial sum formulas. And so I encourage you to just refresh your memory on that. That's going to be useful in this class. So using those formulas, we can get expressions for the two different periods, two different phases, if you like, of this partial overlap. So this is like the partial overlap, and this is the full overlap periods And so we get these two expressions. And the full overlap corresponds to n greater than 9, and partial overlap is 0 up to 9. So we can generalize this example. We can just take a general alpha to the n u of n. So here you have 1 alpha, alpha squared. This is where alpha less than 1, or less than 0. But you could also think about alpha is equal to half, for example, or something like that. And then we're convolving with this box. So what's the first step is to draw a picture. It's always the first step is to draw a picture. I'm going to say this several times in the class, but really drawing a picture helps you visualize what's going on. I think once you have a picture of what's going on, then you can check your algebra against those pictures. Okay, so we just have this same expression now. Instead of going up to 9, going up to 10 minus 1, we're going up to n minus 1. So we just do the same operations that we did before. Again, we're just basically substituting, 9 equals, is n minus 1. So we're just kind of doing the same formulas. So again, we get this summation of this decaying exponential and this triple term delta function. And this triple term delta function is only equal to 1 when k is equal to n minus m. So I can simplify this double summation here. And so we get, again, two terms, this sort of partial overlap. And this is the full overlap. And so we can then use our general formulas that we had from the previous slide on the geometric series to simplify. And we get something that looks like this. So basically this tells you if you want to convolve a exponential, decaying exponential with a box, and the box is of length, capital N minus 1, or total length capital N, so it goes from 0 to capital N minus 1, this is the answer. And you can just do problems where you just plug into the formula here, and then you get the answer. You don't have to do the calculation by hand over and over again. And that's really the power of doing these kind of calculations, like in general, is that, once you have a sort of general formula, you can sort of just apply it when you need it. It's kind of like a template. That's the word I'm going to use, is it's template for solutions. And we'll see how that can become actually quite useful in just coming up. So, of course, whenever there's a sort of method to use, you should try it out on your own. So here are a couple examples for you to try out. And I think when doing these, you might end up seeing some patterns, and hopefully you can apply the general formula and see how it gets used and get some practice doing all of that.